So okay, we were solving the problem on design of cantilever retaining walls, and we have solved up to this step, that is design of or calculation of area of steel reinforcement for your stem. Okay, and we'll continue from this step. We have got the spacing of steel reinforcement for your stem as 100 mm center to center, and uh, now what we have to do, that we have to curtail the steel reinforcement, because so we'll write the step curtailment of steel reinforcement. Okay, the next step is curtailment of steel reinforcement. Okay, now we know that if this is our cantilever retaining wall and this is the stem part, this is the stem part, this is your stem. Now what is happening is that from the upstream side there is some active earth pressure is acting on this particular stem, which is acting at a distance h by 3. It is acting at a distance h by 3 if small h is the height of your stem. Okay, and the value of this pressure, active earth pressure, pH, this is equal to half into Ka gamma h square, Therefore what is the overturning moment which is developed due to this particular force of pH? This will be equal to this pH multiplied by h by 3. Let us consider this is small h. Then overturning moment is equal to, okay, this will be half Ka gamma h square multiplied by h by 3. So this will become 1 by 6 K gamma h cube. Okay, from this particular equation we can say that this bending moment, this value of m0, it is increasing in terms of cube of this h. It is increasing in terms of cube of this h. That is, the bending moment will be something like this. For this stem, the bending moment will be something like this. Okay, that is, it is minimum or 0 at the top, whereas it is maximum at the bottom. Therefore if we are providing some steel here for this maximum bending moment, okay, at this particular location the bending moment will be, let us consider mx. This will be small as compared to mmax. Okay, if we consider some location here, again this bending moment y, let us consider my, it is again lower than mx. Therefore complete steel reinforcement throughout the length is not economical option. Therefore what we will be doing, we will provide some bars up to this particular distance. Let us consider this distance, we will be providing up to a distance of h by 3. Okay, h by 3. Okay, then what we will be doing, we will be curtailing again 30%, will be curtailing here 30% reinforcement, and remaining 30% reinforcement will be curtailing here. So what we will be doing, some bars will be up to this height, that is this height will be again h by 3, this total height will be 2h by 3. Okay, and remaining bars will be throughout the height of your stem, so that we can achieve the economy by curtailment of your reinforcement. So this height will be again h by 3, this will be h by 3, and total height will be h. Okay, this is how we will be curtailing the steel reinforcement. So what we will be doing is that now, okay, so what we will be doing, we will be curtailing the steel reinforcement from for a height of h by 3 from the bottom, then again we will be curtailing 30% reinforcement for next h by 3, and rest of the reinforcement will be running throughout the height of your retaining wall. Okay, okay, now after curtailment of steel reinforcement, what we have to do is we have to provide the distribution steel. So next step is providing distribution steel. to provide distribution steel. Okay, so we have to provide some distribution steel. Okay, so distribution steel, we know that the distribution steel or AST minimum, this AST minimum, this is equal to 0.12 of cross sectional area, 0.12% of your cross sectional area, that is B. This will be your B, okay, multiplied by total depth. Okay, we know that the average depth at the top is 200 mm and at the bottom of your stem is 400 mm. Therefore average depth is 200 plus 400 mm, that divided by 2. So we get AST minimum. We have already calculated this value above also, that is 360 mm square, 360 mm square. So what we will be doing, we will provide half of this steel reinforcement, okay, half of this 360 mm square, okay, on the tension phase of your stem, and remaining half of this 360 mm square on the compression phase. So half of this, that is half 1 by 2, that is equal to 180 mm square on tension phase, and remaining half equal to, that is half equal to 180 mm square on the compression phase of your retaining wall or stem. Okay, this is our retaining wall, and first we have calculated the vertical steel reinforcement. For that we have got some spacing of like this. We are providing some vertical reinforcement, and spacing for that vertical reinforcement was 110 mm square, and now we have to provide the distribution steel. Now distribution steel will be provided like this. Okay, this will be perpendicular to the vertical steel reinforcement. It will be perpendicular to the vertical steel reinforcement, okay, like this. Okay, so what we will be doing, we have got this 360 mm square, so half of this will be provided on the tension phase. This is our tension phase, so half, that is 180 mm square, will be provided on this tension phase as a distribution steel. These bars are our distribution steel, reinforcement. Okay, half will be provided like this, and remaining half, what we will be doing, we will be providing this 180 mm square, okay, on the compression phase, okay, like this. So on compression phase, what we will be doing, we will be again providing distribution steel reinforcement. Okay, this will be in horizontal direction, like this. Okay, so what we will be doing, we will be providing 180 mm square on this tension phase, and remaining 180 mm square on this compression phase, Okay, so spacing for this 180 mm square, this will be equal to, we know that for the spacing, let us provide 8 mm 5 bars. For 8 mm 5 bars, formula is area of 8 mm 5 bar divided by AST, which we have to provide, multiplied by B. We have area of 8 mm 5 bar is pi by 4 into 8 square, pi by 4 into 8 square. AST we have to provide is 180 mm square, multiply this with B. We will be considering B as 1000 mm. So we get a spacing of 279 mm, okay, center to center. Let us consider it is equivalent to 270 mm center to center. So we will be providing steel reinforcement at 270 mm center to center. So what we will be doing, we will be providing these distribution steel reinforcement bars, which are horizontal at 270 mm center to center on this tension phase, whereas remaining one out of this 360 mm square, remaining 180 mm square will be providing on this compression phase, at 270 mm center to center. At the same time, to hold these horizontal steel bars, we must have some vertical or some inclined steel reinforcement on this compression phase. So what we will be doing, we will be again providing steel reinforcement equal to having spacing of 270 mm center to center, like this. Okay, it is not straight. Okay, let me draw some straight bar. Okay, so like this, these bars are again vertical bars 270 mm center to center, and these horizontal bars again 270 mm center to center. Okay, these bars are distribution bars, whereas only vertical bars on the tension phase, these are the main steel reinforcement. Okay, so this is how we have to provide this distribution steel bar. Okay, so in that manner, what we will be doing, we will be providing, what we will be doing is that we will be providing a single mesh on the compression phase and one mesh on the tension phase. Okay, we will see the next step. So next step is design of toe slab, design of your toe slab. Okay, now this is, if this is your retaining wall, this is your cantilever retaining wall. This particular portion, this is called as toe. Okay, this complete portion from this end to this end, it is base slab, and this particular portion is called as a base, hill slab, it is called as a hill slab. Okay, so first we will be designing this toe slab, Okay, so for design of this toe slab, we know that this particular retaining wall, this will be subjected to some earth pressure from the foundation, Okay, this particular retaining wall will be subjected to some earth pressure from the foundation soil, Okay, so we know that we have already calculated the P max, value of P max and P minimum. So we have got this as P minimum was 12.8. This value was 12.8, whereas this particular value was 117.86. So by using symmetry of triangles, we can calculate the value of these values. Okay, we can calculate these values, okay, exactly below this face of your retaining wall. So first we will be calculating this value. Okay, let us consider this is y1 and this will be y2. So y1, how to calculate this y1? We will get this y1. Okay, we have to design this particular toe slab, So for this we must know these two pressure values here. So y1, okay, how we can calculate this? Y1 can be calculated by dividing this particular pressure diagram in two parts. So one rectangular portion, this rectangular portion, and remaining this triangular portion. Okay, so y1 is equal to this 12.8 plus, okay, y1 is equal to 12.8 plus we have to calculate this particular value. This can be calculated by using symmetry of triangles. Okay, this is 12.8, this value is 12.8. Okay, so plus 1.75 divided by 2.5 into this 117.86 minus 12.8. Okay, that is 117.86 minus 12.8. So we get this value of y1 is equal to 86.35 kilonewton per meter square. So this y1, this value is equal to 86.35. Similarly, we can calculate the value of this y2 by using similarity of triangles, and we will get this value as 69.53 kilonewton per meter square. Okay, so these are the values. So now we have to calculate the bending moment which at the face of this particular retaining wall here. Okay, that is at the face of this stem joining this toe. Okay, like at this particular face we have to calculate the bending moment. So bending moment developed will be, first, bending moment due to this 12.8 kilonewton per meter square uniformly distributed load, and some load which is having some intensity like this. Okay, like this. Okay, that is, this value will be 117.86 minus 12.8, and again this value will be 86.35 minus 12.8. okay, like this two different loads will be acting on this particular portion. Okay, so the bending moment M, bending moment developed over this toe slab, this is equal to, okay, the bending moment, just a minute, okay, sorry, there was some mistake. Okay, just a minute. Okay, the pressure acting on this particular toe slab will be like this. Okay, the pressure which is acting on this toe slab will be like this 86.5, this 86.35. okay, this UDL, okay, so 86.35 kilonewton per meter square, this UDL plus some uniformly varying load, okay, having intensity like this. Okay, so for this particular portion, the intensity here it will be this intensity here it will be equal to 117.86 minus 86.35. okay, so for this, the bending moment M, this is equal to the bending moment due to UDL, okay, this 86.35 kilonewton per meter square. So it will be, again, because this is a cantilever, it will act like a cantilever like this. Okay, therefore bending moment will be WL square by 2, therefore 86.35 into, we know that this is 0.75, so 0.75 square divided by 2. okay, plus bending moment due to this particular triangular portion or triangular pressure, this value we have already known, this 117.86 minus 86.35. okay, so half, the bending moment will be half into base is 0.75 multiplied by the value is 117.86 minus 86.35. okay, and it is acting at a distance 2 by 3. It is acting at a distance 2 by 3 from the face of this stem, downstream face of this particular stem. So it is 2 by 3 into 0.75 so we get this bending moment is equal to, you can do the calculation also, 30.19 kilonewton meter, 30.19 kilonewton meter. okay, therefore factored bending moment will be equal to 1.5 into mu. So this will be equal to, okay, put the value of mu here, 1.5 into, we have mu is equal to 30.19, so we get final bending moment or factored bending moment as 45.285 kilonewton meter, 45.285 kilonewton meter. Again, we have total depth of this particular slab, we know this is 400 mm, therefore D is equal to 400 mm. and let us consider a cover of provided for this particular base slab is 50 mm, therefore the effective depth D, provided here, it will be equal to 400 minus 50, that is equal to 350 mm. okay, Now we have to calculate the steel which is to be provided in the toe slab. Therefore steel calculation, okay, we know that AST, we have mu, factored bending moment for this toe slab. This is equal to 45.285 kilonewton meter. We have D is equal to 350 mm. Therefore we know that steel calculation AST is equal to we know the formula 0.5 into FCK divided by Fy multiplied by 1 minus square root of 1 minus 4.6 mu divided by FCK BD square multiplied by again B into D. Put the values here. We know 0.5, we know we are using M20, therefore 20 Fe415 multiplied by 1 minus square root of 1 minus 4.6. we know bending moment mu is equal to 45.285, okay, divided by FCK is 20, B is, let us consider 1000 mm multiplied by D, that is 350 square, okay, and complete term multiplied by B into D, that is 1000, and D is again 350. We get this value AST, AST is equal to, okay, we get this value AST, bending moment is equal to 45.285, there is 45.285, okay, that is 366.5. we get this value 366.36, 366.5 mm square, 366.5 mm square. Okay, we will calculate the AST minimum value. AST is equal to 366.5 mm square. We will calculate the value of AST minimum. We know that AST minimum is equal to 0.12% of cross sectional area. Therefore 0.12 divided by 100 into B into D. So this is equal to 0.12 divided by 100 into B is 1000 multiplied by D is 400. Okay, so we get this value as 480 mm square. We get this value as 480 mm square. Okay, therefore AST is less than AST minimum. Therefore provide AST is equal to 480 mm square. Provide AST is equal to 480 mm square. Okay, now we have to calculate the spacing of steel reinforcement. Okay, so for spacing we know that for spacing we have spacing is equal to let us provide 12 mm 5 bars. Let us provide 12 mm 5 bar. Therefore spacing we know the formula area of 112 5 bar divided by AST provided multiplied by B. We know area of 1 5 bar pi by 4 into 12 square divided by area of steel provided is 480 mm square multiplied by B is 1000. So we get this spacing. Okay, I have just created one Excel formula for this. Okay, so we get the AST is equal to 308 mm square, 235 mm. Just a minute. Okay, so we get this AST of we get this AST of just a minute. Okay, 0.12%. So we get a spacing of 235.5 mm square mm. So we get a spacing of 235.5 mm center to center, center to center. Okay, let us provide this spacing. Let us provide the spacing of steel reinforcement, main steel reinforcement for the toe slab equal to 230 mm center to center, 230 mm center to center. Okay, so 12 number of 5 bars will be provided at 230 mm center to center. Okay, the next step is design of okay, so previous step was step number 6, design of toe slab, and the next step is step number 7, that is design of base slab, design of hill slab. Okay, so step number 7, design of hill slab. Okay, so we'll be designing the hill slab. Now we know this pressure distribution. This is your retaining wall, is something like this. This is your retaining wall, something like this. Okay, and the pressure distribution we have just calculated. This value is 117.86. Here the value is 12.8, and we have calculated these intermediate value. So here it was 86.35 and here it was 69.53. This is the pressure distribution diagram for our cantilever retaining wall. Okay, now for design of this particular hill slab, we know that this width of this particular portion is 1.35 meter, and the height of this retaining wall from this point, it is 4.35 meter. We know that this particular retaining wall is subjected to some force, or some it is subjected to the downward load of this particular soil mass, which it is retaining on its base. So this weight is completely on this particular hill portion. Okay, so it will be providing some resistive force here, or bending moment will be developed due to this load. Okay, this bending moment we have to calculate the value of this particular bending moment. Now weight of this backfill, the weight of this particular backfill material, this will be equal to, we know this formula is gamma into h1. Let us consider this is h1, so gamma value is given 18, and h1 we know this 4.35 meter, 4.35 meter. So we get this value of weight of backfill, is equal to 78.3 kilonewton per meter. Okay, now self weight of this particular portion, we have to calculate, because it will be again providing some uniformly distributed load. Okay, so self weight of hill slab. Okay, this will be equal to this thickness 0.4 multiplied by per meter length, we have to calculate, and multiplied by 25. So we'll get self weight is equal to 10 kilonewton per meter. Therefore total downward load, this is equal to 78.3 plus this 10. So this we get as 88.3 kilonewton meter. We'll just delete this particular portion. Okay, okay, So this particular value of this load, this is 88.3 kilonewton meter. This is 88.3 kilonewton meter. We can write here also, that is 88.3 kilonewton meter. So it will be creating some hogging bending moment like this, that is negative bending moment, whereas this upward soil pressure will be creating the sagging bending moment, that is positive bending moment. Therefore bending moment which is produced due to upward soil pressure and this uniformly distributed load, upward soil pressure and uniformly distributed load, we have to calculate this particular bending moment which is acting on this particular hill slab. Okay, so this bending moment M is equal to first bending moment due to downward load, that is bending moment will be bending moment will be like a cantilever. Okay, cantilever, therefore bending moment is equal to minus 88.3 multiplied by L square. L is here 1.35 square divided by 2 plus bending moment due to this 12.8 kilonewton meter upward soil pressure, 12.8 kilonewton per meter upward soil pressure. Okay, so bending moment due to this 12.8, this will be equal to 12.8 into L square, that is 1.35 square divided by 2. Okay, again plus bending moment due to this triangular load, bending moment due to this particular triangular load. Okay, which is here we have this particular triangular load here like this, which is having an intensity here, this particular value, this will be equal to 69.53 minus 12.8. Okay, so this will be plus, and the bending moment value will be half, base is 1.35 into height is 69.53 minus 12.8. okay, multiplied by, it is acting at a distance 1.35 by 3. Okay, so 1.35 divided by 3, you just calculate this bending moment, we get the value of bending moment here, we get the value of bending moment here. M is equal to we get this value of M is equal to 51.57 kilonewton meter, 51.57 kilonewton meter. Now we have to calculate the steel, AST. Okay, steel calculation, therefore steel calculation. Okay, we know this formula, AST is equal to again 0.5. I will directly write down the values. 0.5 into FCK is 20 divided by FY is 415 multiplied by 1 minus square root of 1 minus 4.6. okay, sorry, I just forgot to convert this into factored bending moment. Therefore mu will be equal to 1.5 into 51.57 kilonewton meter. This will be equal to 77.35 kilonewton meters, 35 kilonewton meter. Okay, so 4.6 into mu is 77.35 divided by FCK BD square. FCK is 20, B is 1000, D is again 350. Complete this bracket, multiplied by B into D, that is 1000 into D is again 350. This will be square. So we get this value, AST is equal to, we get this value 70. Okay, I have just prepared this Excel sheet. We get this value as 77.35. 77.35, 636.4. Okay, so we get this AST is equal to 636.4 mm square. Also we know that AST minimum is value of, this is greater than AST minimum, this is greater than AST minimum of 480, I think, just a minute. Yeah, 480 mm square. It is more than AST minimum, and therefore we will be provide AST is equal to 636.4 mm square. Okay. Now to calculate the spacing of steel reinforcement S, spacing of steel reinforcement S, we have to calculate the spacing of steel reinforcement S. Okay. S is equal to, let us provide phi is equal to 12 phi is equal to 12 mm. Therefore S will be area of one phi bar, that is phi by 4 into 12 square divided by 636.4 multiplied by B, that is 1000. So we get this value. Just calculate this particular value. So we get this. So we get the spacing as 177 mm. So let us consider this is equal to 170 mm. It is equal to 170 mm. And the spacing of distribution steel, the spacing of distribution steel for, we have distribution steel AST minimum already calculated, it is equal to 480 mm, and the spacing will be calculated as 235.5 mm, 235.5 mm. Okay. So we will be providing spacing of 235.5 mm. Let us consider this is equal to 230 mm center to center, 230 mm center to center. So this is how we have to provide the steel reinforcement for the hill slab. Now step number 8. Design of shear key. Okay, why we are providing this shear key? Because the factor of safety for against sliding was less than 1.5. Factor of safety for sliding was less than 1.4. Therefore we are providing some shear key arrangement, Okay, let us consider this is our retaining wall. This is our cantilever retaining wall. So what we will be doing, we will provide some shear key like this, so it will increase the resistance. Let us consider this particular distance. Is A, or this projection is A. So A is the projection of this particular shear key. And also we know this, this pressure distribution diagram. From this pressure distribution diagram, the pressure intensity here at the face of this stem is 86.35 kilonewton per meter square. Okay. Now we know that the coefficient of active pressure we have already calculated. The coefficient of active earth pressure. Okay. This Ka, this was 0.33. This was 0.33 or 1/3. Okay. Therefore coefficient of passive earth pressure Kp, this will be equal to 1/Ka. Okay. This will be equal to, coefficient of passive earth pressure will be equal to 3. Okay. Now we have assumed this particular projection of shear key is equal to A. Okay. Shear key is A. Therefore this particular shear key now will provide some resistance against sliding due to this projection A. Okay. So this resistance offered by this particular active earth pressure. Okay. Therefore resistance offered due to active earth pressure, passive earth pressure, due to passive earth pressure, so this will be equal to coefficient of passive earth pressure multiplied by the vertical pressure. Okay. Vertical pressure. and this vertical pressure is equal to 86.35 into A. So this will be equal to Kp, we have 3, and vertical pressure is this A value multiplied by this pressure at the face of this particular stem. So this will be 86.35 multiplied by A. So this value will be equal to 259.05 A. Okay. So this much pressure will be offered by this particular shear key. This will be the pressure which is offered by this. Okay. Now we know that factor of safety, therefore factor of safety against sliding, okay, this was FS2 earlier it was 0.9 into mu summation of W divided by PH. This was the earlier value, but due to this sliding, due to this particular due to this shear key, the sliding resistance the resistance provided by the retaining wall is increased by, this is increased by this value, that is 259.05 into A. So this will be the final formula for factor of safety against sliding, and we should have this value at least equal to 1.4, at least equal to 1.4. Now we know the most of the values except the value of A here. Just put the all the values here. So 0.9, we have mu is equal to 0.5. We have calculated the value of this summation of W earlier itself, that is this was 163.33 plus 259.05 into A divided by PH. It is also calculated 67.69. So this is equal to 1.4. From this value we can get this value. A is equal to 0.085 meter, that is equal to 90 mm, that is equal to equivalent to 90 mm. So what we will be doing, provide this is very small, therefore what we will be doing, provide A is equal to 200 mm, A is equal to 200 mm. Okay. So this is how the final design is done, and now finally we will do the detailing of steel reinforcement, detailing of the steel reinforcement. Okay. Now we will be doing the detailing of steel reinforcement, that is step number 10. Okay. So this is our retaining wall, sorry, this is our retaining wall, this is upstream face. Sorry. Here we will be having a shear key like this. This is the slant face of our retaining wall, toe slab, and again shear key. Okay. So this particular depth is 200 mm, this particular depth, this is 200 mm, this width is 400 mm. Okay, all dimensions are in mm. Now the vertical reinforcement, the main reinforcement will be on this tension face. Okay, so this is the main reinforcement which will be provided, this is the main reinforcement which will be provided up to this particular shear key. Okay. So proper development length should be provided like this for the steel reinforcement. Okay, and this steel reinforcement are provided at a spacing of, these steel reinforcement are provided at a spacing of 100 mm center to center. Okay, so these steel reinforcement, these are provided at a spacing of 100 mm center to center. Okay, next we have to provide some distribution steel here on the tension face. So distribution steel will be like this. Okay, the distribution steel will be like this, the distribution steel will be like this. Okay, up to this point we have to provide the distribution steel. Okay, and this distribution steel is provided at a spacing of 200 mm 270 mm center to center. This is provided at 270 center to center. Okay, now one mesh of steel reinforcement of 12 mm fibers is required to be provided on the compression face, here on this compression face. Okay, both these are 12 fibers, and on compression face we have to provide a mesh having vertical and horizontal spacing of 270 mm center to center. So vertical slant steel provided here 270 mm center to center, and horizontal steel reinforcement, this will be distribution steel only, like this. Okay, so both these bars, all these bars, this bar, this bar, this bar, these are 12 phi at 270 mm center to center. Now we have to provide the steel reinforcement for the toe slab. Okay, now the steel reinforcement for the toe slab, this is the main steel reinforcement, this is the main steel reinforcement here. Okay, this is the main steel reinforcement provided here. Okay, proper development link should be provided. Okay, it is should be horizontal only. Okay, and some distribution steel is required to be provided. Okay, the spacing we got, the spacing for this particular distribution steel we have got the spacing was, I think, 230 mm center to center. This steel bar 12 phi at 230 center to center, and this steel bar is provided at a spacing of, I think we got this at a spacing of, design of toe slab, this was 200 just a minute, yeah, 235 mm center to, 30 mm center to center. So this is to be provided at a spacing of 230 mm center to center. This is again 230 center to center. Again we have for hill slab, the main reinforcement will be at the top because it is subjected to okay, like this main reinforcement. Okay, it is again provided at some spacing. The spacing, it was I think the spacing we have got, that was 170 mm center to center, 170 mm center to center. So this is 170 center to center, 12 phi again. Okay, and the distribution steel at 230 mm center to center, like this. Center to center, again 12 phi. Okay, so like this we have to provide the steel reinforcement. And regarding the your curtailment, if we see the longitudinal section or longitudinal view of this particular retaining wall, okay, let us consider this is the longitudinal section, then the steel reinforcement that is provided, that will be something like this. Okay, one complete bar at a spacing of 110 mm. Then the second bar will be curtailed from a height of h/3 from the top, like this, and the third bar, that will be again curtailed from a height of 2h/3 from the top. Again third bar will be complete bar. Then we will have some curtailed bar, again we will have some again curtailed bar, one complete bar, curtailed bar, again curtailed bar. Like this we have to provide the curtailment of steel from the economic point of view, and with this R, this is the figure for reinforcement detail. Okay, so with this particular design is completed. With this particular design is completed. Thank you.